Have you ever just paused for a second and wondered about the hidden mechanics behind everyday stuff? I mean, from the stomach-dropping thrill of riding a massive roller coaster to the absolute stunning grace of a ballet performance, there are these invisible, elegant physical rules governing exactly how things spin, turn, and roll around us. Well, today, we're going to uncover the completely fascinating world of rotational dynamics. We're going to look right past the complex, scary equations and explore exactly how these fundamental principles dictate the motion of our entire world.
So let's start with a question just to get our gears turning. You've absolutely seen this before. A figure skater or a ballet dancer is out there spinning, and then suddenly they pull their arms tightly into their chest. Instantly, they become this complete blur, spinning so much faster. I mean, why does this happen? It honestly looks like magic, right? But it's actually pure physics. It's an invisible rule in action. And by the end of this explainer today, you'll know the exact mechanical secret behind this trick.
To get there, here's our roadmap for today. 1. Basics of circular motion. 2. Forces behind the spin. 3. Moment of inertia explained. 4. Conserving angular momentum. And finally, 5. The physics of rolling. Okay, let's dive into this with section 1. Basics of circular motion. Think about a ceiling fan for a second, or even just a wheel on a bicycle. When an object moves in a perfect circle, even if its speed is totally, perfectly constant, it's actually constantly accelerating. Now you might be wondering, wait, why? Well, because in physics, acceleration isn't just about stepping on the gas or hitting the brakes, it's also about changing direction. In circular motion, the direction of the object's velocity is literally changing at every single instant, tracing a path that's tangential to the circle. Now, to actually visualize the direction of that spin, or what physicists call angular velocity, we use something called the right-hand thumb rule. Literally, take your right hand right now. If you curl your fingers along the sense of rotation, the way the object is spinning, your outstretched thumb points in the exact direction of the angular velocity. It beautifully anchors the abstract math of vectors into a physical spatial reality you can map out with your own hand. Moving right along to section 2, forces behind the spin. So what actually keeps these objects moving in a circle in the first place? Like, why don't they just fly off in a straight line? Think about a roller coaster in an amusement park. When you go flying through a vertical loop, you experience these changing normal reaction forces at different parts of the track. These forces are actively keeping you on that circular path, preventing you from just launching in a straight line off into the sky. The specific force responsible for this inward pull is called centripetal force. And I really want to be clear here because it's super commonly misunderstood. It is a strictly radial force providing acceleration towards the center of a circular path. It continuously changes the direction of velocity without changing its magnitude. Just picture a tiny stone tied to a flexible string, being whirled around in a vertical circle. The tension in that string, that's the centripetal force. It is actively pulling that stone inward, directly toward the center, at every single moment. Which brings us to section 3, moment of inertia explained. Now, let's shift our focus from the forces that cause spinning over to an object's natural resistance to being spun. Imagine you're trying to push open a really heavy door. If you push it right near the hinges, it requires a massive amount of effort and force to get it moving. But if you just push it at the outer edge, far away from the hinges, it opens super easily. This everyday experience introduces us to this incredible concept of rotational mass. And this brilliantly illustrates how every linear rule we intuitively know has a direct rotational twin. Linear mass becomes moment of inertia, linear force becomes torque, linear velocity is angular velocity, and linear momentum translates perfectly to angular momentum. The math completely mirrors itself, literally translating our straight-line world into a spinning one. But wait, here is the absolutely critical difference. Moment of inertia depends on two fundamental things: the individual mass and exactly how that mass is distributed around the axis of rotation. It's not just about how heavy the door is, right? It's about how far that heavy material is from the hinges. The further the mass is distributed from the center of rotation, the greater the moment of inertia, and the much, much harder it is to start or stop the spin. All right, section 4, conserving angular momentum. This brings us to a massive, fundamental concept in physics, conserving angular momentum. The principle basically states that if no external unbalanced torque is applied to a system, its angular momentum remains entirely constant. And guys, this finally answers our initial question about the ballet dancers.
When they pull their arms in, they are instantly decreasing their moment of inertia because their mass is now way closer to the center of rotation. But because their overall angular momentum absolutely must stay exactly the same, their angular speed has to increase to compensate. Therefore, they spin faster. It's amazing. Let's see the same high-speed mechanics in action with a diver in a swimming competition. Step 1, the diver jumps off the board and stretches out their body, maximizing their moment of inertia. Step 2, immediately they fold their body tightly, drastically reducing that moment of inertia. Step 3, because angular momentum is strictly conserved, their spin frequency instantly spikes, allowing them to complete multiple thrilling flips in the air. Step 4, just before hitting the water, they stretch out again, increasing their inertia, which rapidly slows their spin for a perfectly smooth, streamlined entry.
And, it's not just human bodies performing these tricks. It's quite literally a universal law. We can prove this mathematically with this classic, fascinating textbook problem. Just imagine a spherical water balloon rotating at 60 revolutions per minute. Over time, it slowly leaks exactly 48.8% of its water, so almost half. Because both the mass is lost and the physical radius of the sphere shrinks, the entire distribution of the mass changes. By applying the exact same conservation of angular momentum we just talked about, physicists can calculate exactly how the frequency of rotation adapts to that specific mass loss. Because the radius and mass distribution decrease, the rotational speed must mathematically increase to keep the whole system in perfect balance.
Let's move to and see how this builds into our final concept, Section 5, the physics of rolling. Pure rolling is basically the ultimate combination of everything we've discussed today. It equals rotational motion around a symmetric axis plus purely translational motion of the center of mass. When an object like a cylinder or a wheel rolls without slipping, what we call pure rolling, it is beautifully executing two distinct motions at the exact same time. The object itself is spinning around its own axis, while its center of mass is simultaneously gliding forward in a perfectly straight line. It is this brilliant, elegant marriage of linear and rotational dynamics playing out right in front of us every single day.
So, I really want to leave you with this provocative thought. Next time you drive down the road, take a moment to look at your car's wheels. How do the hidden rules of linear and rotational dynamics work perfectly together to propel you forward? Physics isn't just some abstract concept trapped in textbooks or complicated equations. It's literally the hidden engine driving the world around you. Every spin, every roll, every turn follows a script. Keep observing, keep questioning, and I'll see you in the next explainer.